It's a pleasure to be here, so thanks for the opportunity. Knowing that I was going to be talking after a number of people talking about Accelerator Mass Spectrometry, it's always a question sort of what level of detail and what should we include. So what I thought I would do is play some fun with some word games. The dating game would be one of them, because I think to a certain extent that's what we're into when we're looking at environmental isotopes. But we really want to apply those new tools to some interesting questions. So in this talk, what I'm going to do is sort of explain to you, first of all, how disappointed I was to realize that the University of Ottawa doesn't even rank on dating sites when you go to the internet. Those are the top 6 or 8 sites in Ottawa, and we're not one of them. So you might say that our goal is to sort of replace those sites with, our site, at least on Google Maps. So when somebody looks up dating and finds out how important it is in science, that we would be up there as well. And I think we have an awesome opportunity to do that with the new Advanced Research Complex and our new facility that's there. So that's the long-term goal. So short-term goal here today, what I want to sort of explain to you is sort of the ABCs of a different type of radionuclide, some of those that are produced in situ along the lines of what Matt was just discussing. I'll explain why accelerated mass spectrometry is so important and to open up this whole field of science. And then I'll give one example of what I call a closely knit couple, looking at chlorine-36, chlorine-35, and how we can apply that to an interesting geologic question about nuclear waste management. So Rutherford's the guy who worked, first of all, to work out the concept of radioactivity, discovered that there was this thing called an alpha particle. When he wrote his Nobel acceptance award, he wasn't even sure that it was an alpha particle. So obviously over the past 100 years since he got his Nobel Prize, we've elaborated on all that, and people are using uranium-235, 238, and various other isotopes that are still kicking around on the Earth. And we tend to think of the Earth as being radioactive because it has these decay series, like the uranium-238 decay series, and all of those progeny isotopes that Anthony and other people talked about. But in reality, if you sit and think about it, that's only a small fraction of what's produced. Really, the diversity of radioactivity is a result of in situ production, both in the geosphere and in the atmosphere. So we have big quantities of uranium and potassium that have been there since the Big Bang, but the continual production across a diversity of isotopes is really what I would argue gives us as geoscientists the opportunity to use these as tracers in a whole variety of different approaches. The classic one that you've heard about is carbon-14. We have carbon-14 on the Earth simply because of the fact that there's nitrogen-14 in the atmosphere. And there's also nitrogen in rocks. And there's other ways that you can make carbon-14 in rocks too. But we produce it by basically hitting it with a neutron. These neutrons coming from these cosmic rays that come from both our solar system and further out in outer space. And we produce carbon-14. We continually produce it. And that's the basis for carbon-14 data. But there's hundreds, if not thousands, of other reactions that go on both in the atmosphere and in all our rocks. And not just the rocks close to the surface, but they go on in all the rocks all the way down. And if we could measure those few atoms, then we have an awesome tool that covers across the whole periodic table. So thinking long term, thinking big, we'd like to be able to measure as few as 10 atoms, say, in any sample of rock or any other material that a geologist would like to study. And we'd like to do it across the whole periodic table. So, small ambition. Long time to work on. But it'll keep us as scientists employed for a long period of time. Okay, so I'm radioactive because I've got all this stuff inside me, so are you, so is the Earth, and the key point is that we can take advantage of these, and that's really what we're doing when we're using the Accelerator Mass Spectrometry facility at the ARC. Because these are just, I've circled here just some of the isotopes that we're interested in and using right now, but my argument is there's all these others as well that we could take advantage of. We just have to figure out analytically how to be able to measure them. And Accelerated Mass Spectrometry at the moment offers the best potential for a lot of these. So conventionally as a radiochemist, which is really what I am, masquerading sometimes as a geoscientist, I have basically been measuring the emissions. That's the radioactive decay part, the alpha, betas, and gammas that are emitted from a radioactive atom. And there's a whole bunch of different ways that we can do this. You can do it like in situ if you're worried about contamination, the sorts of situations that Matt was talking about. You can do it with conventional counters. And if you really want to get sophisticated, you can go to the Sudbury Neutron Observatory, SNO, and you can measure the square root of nothing up there because it's so clean and so low and so deep down in the Earth, really clean granite. So that's why they put it up there, and we actually worked in the past on some of the materials there to make sure it was really clean. But basically, you get your background down, you can measure pretty much any kind of decay that you want. But that ignores the fact that the vast majority of atoms sitting in front of your detector are not decaying. So this is the law of radioactivity, as Rutherford elucidated it. And if you just sit and think about this for a couple seconds, you'll realize that dNdt, that's the rate of decay, is proportional to lambda, our radioactive rate constant, times the number of atoms. And there's inverse proportionality, obviously, there between the two. And half-life is just ln 2 over the, or sorry, lambda is just ln 2 over the half-life. So if you're used to thinking about it in terms of half-life, just put half-life down there in the denominator. The bigger the half-life, the more atoms we have, the fewer decays we have. For a short-lived isotope, we got lots of decays. Lots of disintegrations of those atoms, but we don't have many of the atoms. For something that's long-lived, we got lots of atoms and not very many decays. So most of the periodic table that we're interested in as geoscientists is sort of falling in this area over here. If we're interested in short-term things, but if we're interested in long-term things, that's where we want to be. So do you want to measure atoms and ions, or do you want to measure decays? Well, here's an example of sort of how we traditionally in science applied that. So if you're interested in uranium-238, it's got obviously a very long half-life on the order of the age of the Earth. There's lots, and a typical sample, I've expressed here how many decays you have. A decay to a radiochemist is described as a becquerel. He was a famous scientist, hence a becquerel is 1 disintegration per second. So in your typical sample of, say, I go out and collect some garden soil, I'd have about 0.01 becquerels. So for every 100 seconds, I get 1 decay. On the other hand, that's 10 to the 15 atoms. That's a huge number of atoms. If I could count those atoms, I don't need to worry about the fact that I might need to count for 100 seconds for 1 decay. I can count those in a fraction of a second. And in terms of mass, that's just converting it from numbers of atoms to number of nanograms or femtograms in the case of Fg. So for radon and lead-210 that have a very short half-life, you can see you've got lots of becquerels, easy to make the measurement, but you've still got some femtograms here too, and maybe that's a better way to go. We've got 48 million atoms, 100 million atoms, and yet we only get a few decays, i.e. 0.1 decay, 0.1 becquerel in your typical sample. So that's why mass spectrometry offers the potential to open up this whole area of science for geoscience. So why isn't it taken over? Well, we'll see in a few minutes. There's a few complications, you might say. The chemistry or the physics gets in the way occasionally. But some isotopes, like chlorine-36, there's really only one choice. There's so few decays in the sample that basically if you can't measure it this way, you can't measure it at all. And that's really where the breakthroughs in accelerator mass spectrometry came first. It's with these isotopes where there isn't any choice. There's just not enough decays. You want to go after the atoms, and that's really what drove accelerator mass spectrometry forward. There wasn't any other choice. So AMS is basically sputter source mass spectrometry. We take a solid sample, we sputter it with cesium, and we basically produce this set of negative ions. If we're talking about chlorine, we can strip off all those electrons when it goes through the terminal. And what that does is it gets rid of all the molecular interferences that conventional mass spectrometry suffers from. So by that I mean we've got this, say, a molecule that's got exactly the same mass to charge ratio as chlorine-36 going into our mass spectrometer. If we run it through the terminal on a tandem accelerator, which is located right about there, and we change its charge from negative to positive, we strip off the electrons. And those electrons, if you think back to your chemistry, those electrons in that outer valence shell are the thing that is keeping together that group of atoms to form a molecule. If you strip them all off, the molecule basically goes boom, and it's gone. And really that's a breakthrough at AMS. And physicists knew about this back in the 1930s, but they hadn't added up the dots to say, oh, if I can do that, then maybe I can measure some of these radioactive atoms that are really rare. When they did discover it, Ted Litherland and his colleagues at Toronto and Rochester back in the 1970s, that's what basically opened up this whole area of accelerated mass spectrometry. So we have some velocity filters as well that are kind of conventional in mass spectrometry, and that get rid of the stable isotope tails because their typical sample has much more of the stable isotope and all these other interferences than it does of the rare isotope that you want to measure. So for example, there's a lot more sulfur-36 in the world than there is chlorine-36, and that's isobaric. And if you, we can separate those with a really high resolution mass spectrometry, but we throw away all our signal and we wouldn't be able to make the measurement. So we have to figure out, even with this type of sophisticated mass spectrometry, how to get rid of these isobaric interferences. And one way is just to fill a gas-filled magnet and take advantage of the fact that relativistic velocities, there's a different number of protons, in a sulfur atom versus a chlorine atom, and you can take advantage of different cross-section that produces when you run them through a gas-filled magnet that has a couple of torr nitrogen in it. So then you can use some conventional physics techniques that they've been using since the 30s, more or less, to detect these atoms using time-of-flight mass spectrometry and residual energy analysis. And if you do that, you can measure things like chlorine-36. It's got a half-life of 300,000 years. To put this in perspective, a sample would give us 300 counts in a year. Those of you who've worked with me know patience is not one of my strong points. I'm not prepared to sit and watch a counter count 300 counts for a year. That's one a day. That is boring. It's like watching paint dry, only it's slower. On the other hand, AES measurement with our new system that's just been installed here in the ARC takes less than 5 minutes. So AMS wins hands down for these rare isotopes, even when there's 10 to the 15 times more stable chlorine than there is chlorine-36. Even when there's 10 to the 15 times more sulfur-36 than chlorine-36, we can still make that measurement. And we can detect about 1 atom in a ratio of 10 to the 15 atoms, and detect less than 1 million atoms of chlorine-36. So we're getting down to that point where we can explore all different parts of the periodic table, and chlorine is just one example. So let's turn this into a question of how we can use in situ production methodologies to do some dating with a geologic example. Decay dating, that's what Rutherford did. That's what carbon-14 ages are based upon. You start out with a certain amount, it goes down over time. My point to you is that the vast majority of the Earth has all these other production reactions going on in all our minerals, in all of our surface deposits, in the atmosphere, and basically we can take advantage of this because we can calculate how rapidly these isotopes are produced, and then we can basically look at the increase as opposed to the decrease to get our dating technology. So chlorine-36 is an example of that, and there's some other things that you can do with other types of dating techniques, but let's focus on this one between now and lunchtime. And I am sensitive to the fact that I am between you and lunch. So I edited this talk substantially to make sure that I am not holding up lunch. So let's take the example of radioactive waste management. This has been a controversial topic. Some people would argue it's the Achilles heel to the nuclear industry, where I've worked in the past. Other people would say it's a non-issue. Well, this is the theory. You take that radioactive waste, you basically make it into a stable waste form. There's a bunch of different ways to do that. You put a bunch of engineered barriers around it, some of which are as simple as bentonite clay. And then you've got the natural barrier if you bury this on the geosphere in some type of plutonic rock on a Canadian shield, or if you put it in some type of other type sedimentary rock. So that's the concept, that's the idea behind it. But can you contain it for 10,000 years? How would you prove to somebody that that's true? You know, you do an experiment in the lab and it lasts 3 weeks. And they look at you and say, well, you know, sure, it worked for 3 weeks, but is it going to work for 10,000 years? It's going to work because these isotopes have long half-lives. They might be dangerous for longer periods of time. So the theory doesn't sort of match with the public's desire for proof. So one way to do that is to sort of say, okay, let's take the worst case. Let's look at chlorine-36 because it's incredibly mobile. It's a chloride ion when it's in water. Very mobile as water. And let's say, whoops, how did I do that? Let's see if chlorine leaks out of our waste material. So to do this, I looked for an analog situation. A situation that's analogous in geologic structure to the types of waste management facilities that were proposed, and one that would produce chlorine-36 itself. So I'm using a natural tracer experiment. And that natural tracer experiment was done at Cigar Lake, which is one of the enriched uranium deposits in the Athabasca Basin in northern Saskatchewan. And there's a number of talks that I can publicize, like Mary's and others, that are talking about various parts, not necessarily Cigar Lake, but all of the uranium deposits in northern Saskatchewan. So I'm going to skim over the geology because they can explain it better than I can. But I'll focus on the waste part of it. So I would argue that Cigar Lake, this uranium mine, is a natural analog to a deep geologic repository. And this was the way Ian described it so eloquently in one of his talks in a cartoon, and so I stole it from him. Theft is equivalent to flattery, right? So we've got the Canadian Shield, the bedrock down at the bottom. We've got this ore deposit here just at the contact point there. And so that's like our spent fuel. We've got clay that's produced from the natural alteration of the sandstone material. So there's a lot of bentonite clay, which is very similar, and there's illite in there as well. There's a number of clay types that are found in Cigar Lake, as in the other natural analogs up in northern Saskatchewan. That's like our bentonite clay. We've got the altered sandstone around it. There's an alteration halo around every one of these deposits that's substantial, and that's sort of analogous to the backfill. And then we've got a quartz cap, which looks pretty impermeable, except for all the fractures running through it that nature's caused over the last 1.3 billion years since the deposit was in place. So you've got the potential to cap it, but you've also got the potential that it's open because of the fact that we've got all of that fracturing that's going on. And then this would flow into a sandstone aquifer, which is basically the far field system that is of concern when you've got a geologic depository. So how can we use chlorine-36 and how can we use our in situ dating? Well, we can use it to basically say, what happens if the chlorine goes through the system and out and picks up some neutrons in there and gets irradiated? It's going to form chlorine-36. So this is the concept. The water flows through. We know where the gradient is. It flows into the ore. It picks up neutrons and basically flows out if the system's open, or it stays there and gets irradiated over time if the system is tight and if there's no flow through it. So to conceptualize this even more, we take a chlorine-35 atom, we run it in, it sees a neutron, it picks up chlorine-36. The longer it's there, the more neutrons it picks up, the higher the concentration of chlorine-36 relative to chlorine-35. Eventually, it will reach equilibrium where there will be decay of the chlorine-36 with its 300,000 year half-life will be equal to the production rate. So if it stays there in round numbers, in radiochemical terms, if you go through 5 half-lives, your production and decay are about equal. So if the chlorine-36 is in that deposit, if the chlorine-35 is in the deposit for 5 times its half-life of 300,000 years, so 1.5 million years, then you would have the same concentration in the deposit as you would expect from production. If there's less, then the chlorine sits in that deposit for less. So it gives us a really nice tool to test not only over a period of 10,000 years, but over a much longer period as well. So that's the hypothesis, that's the sort of the theory behind it. So what do we do? Well, we measured groundwater concentrations, went up to Cigar Lake and pumped out before they flooded it, before they mined it, and all that, right from the middle of the deposit and from all the way across the deposit. So this is basically from the upgrading edge all the way through to the center of the deposit. It's an ingrowth curve, so this is age in thousands of years here, all the way up to the highest samples had chlorine-36 ages that would be 250,000 years. And this is basically the concentration of chlorine. I expressed it as clues here because I argued that some people were clueless, but it really stands for chlorine unit. So this is just sort of units as a radiochemist would describe them. And the uncertainty bars are shown here, and there's just a couple of different simulations that I did depending upon the assumptions you make about how much chlorine you get from a rock itself. So you can look and say that the ages that we estimate here are from about 20,000 years, right, as you go into this deposit, as the water goes basically down the hydrologic gradient through the deposit, you get up to about 250,000 years. So the chlorine is going through this deposit in about, because this is the middle of it, and then it flows out the other end, and unfortunately we didn't have access to ore samples and water samples from further to the other end of the gradient, but it's getting about, by the time it gets to the middle, it's about 250,000 years that your typical chlorine atom is present in this deposit. So it's not moving very fast. If you turn this calculation into a classical sort of Darcy hydraulic conductivity calculation, like I'd like my GO 111 students to be able to do, you work that out, it's moving at the rate of diffusion. Now you could say that, okay, you've looked at the bulk deposit. What happens if you go and look at the areas where there really are fractures going through the system? So we took some cores, and this is from one borehole 220, and I apologize that for whatever reason this projector seems to bias the colors relative to what I see in my computer screen. So this is from the top basically of the core all the way down to the bottom. This is bedrock in here, and it doesn't sort of show up very well. The white layers are clay. The black layers are almost pure uranium oxide. And the stuff that shows up so beautifully on the computer screen as brown, you can see a little bit of it here, a little bit of it here, and a bit here, but it looks really brown on the computer screen that I have. That's stuff where there's been fractures and fracture fillings going on. So what we can do is we can take these different samples in the same way we looked at the water, we can look at the rock and say, okay, we can calculate how much chlorine-36 should be in this deposit based upon the neutron flux. And we can say, do we see in the rock, right in the fracture, chlorine that is what should be there from a 1.5 million year half-life, or do we see chlorine that's there from a much shorter time period, implying that it's been moved over time? And this is a plot of the predicted chlorine-36 concentration, so from that calculation, what should be there theoretically. There's no fit to any model or anything here, it's just basic neutronics against what we actually measured. And I've expressed it in these same clue units, but I've shown you this time that it really means 1 times 10 to the minus 12 is an atom ratio. So the 1-to-1 line is shown here. You can see the points all fall right along the 1-to-1 line. There's a few that fall a little bit further off. In these situations, the measured concentration is a little bit higher than what we actually predict. But you see the vast majority of them fall sort of pretty close to the 1-to-1 line. If I put confidence limits on these from the predictions, given a little bit of uncertainty about how many neutrons were actually produced in this type of material and what the energy spectrum of those neutrons were, basically all of these points, with the exception of this one and this one, would fall within the 1-to-1 line. So what we predict in the ore is what we actually see. In other words, it's at equilibrium. It's been sitting there for at least 1.5 million years to pick up that many neutrons to produce that much chlorine-36. And the other thing you can see is if we were asking questions about the individual rock strata, the ones that are labeled U are the uranium-rich parts of the ore deposit. The ones that are labeled ore were samples that sort of had 10% uranium. The U ones had sort of 50% plus uranium in the rock. The ones that are labeled down here as R's, this, are ones where I thought, based upon the fact that they look like they've been altered, they're smashed up rock, they're rubble zones. So R really stands for rubble zone. Those are the ones that I thought I would see a bias where our predicted values would be much different than the measured values because there's been water flowing through the system, removing the chlorine from the rock. These are all the fracture fillings. And you can see that the fracture fillings, if anything, fall closer to the 1-to-1 line than some of the other samples. So why don't these samples fall way up? Why don't they fall right on the line? We can get into a discussion about that afterwards, but the quick, simple answer is this deposit is incredibly stratified. And it's really tough in some deposit layers that are only, say, 2 centimeters thick to get exactly the estimate of the number of neutrons that a chlorine-35 atom saw. So we are probably biased on that. Our prediction is probably biased low because it's so difficult to estimate the exact neutron flux when there's that much spatial variability in the system. So there are lots of other applications of chlorine-36 that I mentioned in here. There are lots of other applications, and I would argue geology is just starting to take advantage of all of these radionuclides that are produced in situ. We can basically take advantage of the whole periodic table if, for every isotope that's there, it's got a long half-life, if we can figure out how to solve the analytical challenges and get rid of those interferences that initially prevented radiochemists from measuring chlorine-36 for the first sort of 40, 50 years since it was discovered. There were, up until 1980, there were basically 3 measurements of chlorine-36 in the world. And after 1980, there's probably 300,000 for all kinds of different applications, of which I've just shown you one here. And my argument to you would be that we're going to see the same explosion across all other elements of the periodic table driven by accelerator mass spectrometry and other subsequent techniques that will actually eventually replace AMS. So to sum up, I've tried to argue that nature is radioactive. It's radioactive because not just of the uranium and thorium decay chains, but because of all the other stuff that's produced. And we tend to forget about that huge diversity of things that are produced, carbon-14 being a classic example. And these are really useful because they're produced throughout the geosphere, throughout the biosphere, throughout the atmosphere. And we can take advantage of these. And then AMS offers this opportunity to basically strip away all of the stuff that might masquerade as those rare isotopes and allow us to make a quantitative estimate in the presence of all kinds of different kinds of background. And then I tried to illustrate with chlorine-36, one of the most mobile nuclides, to use this to show you that in the case of a long-term test of the hypothesis that waste management works, clearly the chlorine-36 example shows you that that material is very immobile, even in the situation where you're talking about what most people would consider a very mobile chlorine atom. So I hope that we'll be able to exploit the ARC. We're not into it yet, but we're almost there. This is the foyer right outside. This person is supposed to be looking in and admiring our new mass spectrometer. Soon you will all be able to look in there and admire it, just as we have been as we've been commissioning it over the past few weeks. And I hope that this will basically lead to an explosion in the use of these in-situ produced radionuclides. Thanks very much.
The Cornett versus, so it was what you would expect versus if it was actually mobile. Did you plan to perform that experiment another time? Because the data that you showed was, I think you made a reasonable case that it was no larger than the background. However, when it comes to radioactivity, people sort of take that almost akin to Count Dracula.
Yeah, you got it.
So
I am Count Dracula, yes.
Yeah, no. So my point though is that another experiment might hammer in the nail.
Yeah, okay. So I showed you the results for chlorine-36. I stripped down to talk, some of the other sort of nasty radionuclides that people are interested in. We also looked at. So we looked at technetium, specifically because it's one of the things that comes up in waste management, but also because it's very mobile. It's a protected anion. We looked at neptunium, ditto, same sort of chemistry. We looked at plutonium, and we looked at iodine. And again, none of them were mobile. Let's see.
Alrighty then. Oh, questioning?
Oh, sorry to go on.
Bonnie, and you're between people and lunch. Think about that.
So Jack, you look at some of the green plutonium and the actinides, and iodine, also very long-lived. Did you look at any short-lived secular equilibrium for something like radiocarbon?
We did not look at radiocarbon. We could, but we didn't. So the shortest lived thing we looked at was probably, well, we looked at things like lead-210 and things like that, and they're obviously in secular equilibrium, so that doesn't count. Looked at radon. You can see lots of radon, obviously, as an inert gas, noble gas. So we looked at that part of it. Carbon-14 we did not look at. I'm trying to think of the shortest lived thing that we looked at. So we probably didn't look at anything sort of with a half-life that would be in the thousands of years. Everything we looked at was sort of 10,000 years and beyond, because plutonium, one of the plutonium isotopes would fit into that category. So nothing between sort of like 1,000 and 10,000 years.
But the radioiodine is interesting there.
Yeah, but the radioiodine, like, it's a 17 million year half-life. So that, again, integrates over a much longer time period, because again, radioiodine will be integrating, you're getting a signal of production over, in round numbers, 5 times 17 million years. So a very long time period. So everything that we've measured indicates that even in like those deposits which have been glaciated, deglaciated, et cetera, multiple times, subject to multiple fracturing and things like this, you still see all the radionuclides present in the uranium ore that you would expect to see there.
At secular equilibrium.
At secular equilibrium, meaning that production and decay are balancing out and there's no big losses. So the water may be going through the deposit, but it's not leaching very much of anything, even a mobile chlorine ion.
Anyone else? Bill?
Like in sedimentary rocks, you're commonly looking at the paragenesis, the timing of various kinds of cements, which came first, second, third, and all the way through. Would these kinds of techniques be possible at, the menisci around a grain? Would there be ways of using AMS technology to back out the timing and actually give it a date?
Yeah, absolutely, because like if you can separate that, then, as an example, we can go and look, like, if you were separating it, if there's any uranium there and thorium in the deposit, it's going to produce enough neutrons to activate material. So there will be chlorine-36 produced in your sediments if they have any chloride in them at all, as an example. So yes. So the question is then, can we make the detection limit sufficiently small to actually measure right around the 1 grain that you would like to do? So we can talk about how to do that. The answer is yeah.
Anyone else?
Do you see a large pressure differential between your ore body and the pressures that you would measure inside the fractures?
I did not measure that. You can answer that for any other deposit?
Would the fluid flow not be dependent on the
So,
pressure?
well,
gradient?
yeah, fluid flow is dependent on the pressure gradient. So the answer is, yeah, we measured the hydraulic head and the head distribution. So what I did through the Thorny 36 study was started sort of upstream, like well above, like 2 kilometers from the ore deposit, up gradient, and sort of moved through the deposit to where we had boreholes, right through into the middle of the deposit. And so we followed that pressure gradient there, and that was down the hydrologic flow path. But like, so was, like, I was sort of misinterpreting your question maybe. If you're asking how much overpressurized was it, I don't remember. They were at positive pressure, but there's a nice flow gradient into the open end, sandstone aquifer. So there's a regional flow system there. It's not like there's zero gradient and no pressure gradient for flow. So there is a flow gradient, but it's not like really overpressurized inside the deposit.